Christian Graf from GSI. Thank you, Chris, for being with us and for giving us your time in your very filled up schedule. Christian will be giving us a talk about moving targets and precision 4D delivery and ARC delivery. A few words of introduction. Christian Graf received his PhD in biomedical engineering at the Hamburg University of Technology in 2010. Since 2012, he is the group leader of medical physics in the biophysics department of GSI in Darmstadt, Germany. And since 2018, he is the deputy scientific director of his department. And since 2021, professor for technology of radiotherapy at the Technical University of Darmstadt in Germany. His main research interests are advanced treatment planning and delivery strategies for particle therapy, in particular for moving targets. Dr. Graf devised 4D optimization strategies for conformal motion mitigation, which his group implemented in treatment planning and dose delivery systems. Dr. Graf has published 50 peer-reviewed manuscripts and more than 100 conference contributions. Thank you for being with us. It is a pleasure to have you. I give you the floor.
Thanks, Nicholas, for the introduction. I will share my screen. So I think you can see it. So I shortened the title a bit to precision particle therapy, but the topics are more or less as Nicholas announced them. So, okay, why precision therapy? What do I mean with this? Yeah, I think you now heard a lot about Bragg peaks and what ions are capable of, and I guess some of you are also very experienced in ion beam therapy. And so my view is that that basically for most applications, the TCP, so the tumor control for photons and particles, is actually the same, or is at least aimed to be the same, because typically it's already pretty good. But the NTCP is something where particles with their conformity could be a lot better than photons. Yeah, so this is what we should aim for. And in other cases where the TCP of photons is not good enough, it's typically limited by excessive complications in the normal tissue. And so again, here particles could provide conformer therapy and then could increase TCP by dose escalation. And all of this requires that we strive to really maximize the benefit of particle therapy. And this is just an example where this already basically happened, where you have this is a scanned delivery of protons, this is a passive delivery of protons, and this is for comparison a photon plan with an arc therapy, so state-of-the-art photons. And the point that I want to make here is that basically everybody now uses scanned delivery just because it's more conformal. Yeah, you could argue, okay, maybe this plan is not the most conformal ever, but definitely it's much better than the passive delivery was. Yeah, so there are some other benefits for active, but I think the real seller was the increased conformity, and every newly built clinical center now uses this. So, but still, if we look at what happens in the clinic today, then basically the uncertainties, especially in these tumors external to the skull, the uncertainties are very high, and they are compensated by just using large margins. So this is an example plan of that I guess was actually planned and delivered with protons to this lung tumor here. And this is just a planning example. What would be the difference if you just remove the entire safety margins? So you just concentrate the dose to the CTV that you actually want to irradiate. Yeah, and I think the difference between the two is really striking. Yeah, so and if we can do anything to go from this left image to the right one, then this would really benefit the patients. Yeah, so I think that you see here in this field, the heart gets a tremendous amount of dose. A lot of the lung volume is actually in the target dose area. So I guess that this patient would have severe, or at least a good chance of severe complications and late effects. So as Nicholas announced, I'm working on beam delivery and treatment planning. So I will tell you a bit about my work or my topics in this area. And all of them basically focus on increasing conformity and thereby improving NTCP. And as a caveat, I'm not working in a clinical facility. Yeah, so this is sometimes a bit, let's say, aggressive. Yeah, and I think that people in the clinics would probably say that this is not reasonable, and I would say that this is not reasonable yet. Yeah, this is research, and I think we need to see what is possible with particles also beyond next Tuesday, and what we can do in the coming years to really basically keep ahead of photons, which are also getting better and better. Yeah, so we really have to move the goalposts to explore the maximum benefit of particle therapy. So I will give three examples. One of them, streamline of moving targets, aiming for more conformal delivery. Then one is flash, which I guess you probably heard about in the week. I will give a bit of a delivery point of view on this, yeah, and also particle arc therapy. Yeah, I guess you know that in photons, arc therapy, so the rotating gantry around the patient, is just the state of the art. And I think that at least for some special cases, the particle therapy could also benefit from this technique. So the first topic is moving targets. Yeah, why is this important? So this is a cancer statistics from Germany. I just translated all the red ones, which are the cancers affected by motion. This is cancer incidence, and this is cancer mortality. Yeah, and if you see the difference, okay, there are very common moving cancers, but they are even more deadly. Yeah, so in males, this is number one. In females, the lung cancer is number two, and is still rising in Germany, unfortunately, because we are not so efficient in reducing the smoking rate, especially in females. So they are unfortunately catching up to the somewhat more stupid male smoking population. But all of these that are marked in red are tumors that are moving while the beam is on. Yeah, so if we don't have an efficient strategy to cure this or to treat this better as we are currently doing, then these numbers will stay high. And this is very relevant because this is a very large number of patients. And this is, again, just the reason. Of course, this is a photon plan, this is a carbon plan, and you can just appreciate the large difference, especially for this case, patient where basically the heart here would get significant dose and here it gets no dose at all, if we manage to really go for this aggressive small margins approach. And what is actually the issue of particles and moving targets? Yeah, of course, the target is moving, so you could just miss it. Yeah, that's the same issue with photons, but there are some added wrinkles. Yeah, so this is a bit of an extreme animation of this, where you have this solid tumor mass moving in the lung, and it's the same single energy proton beam that either is stopped in the tumor or just passes it by and penetrates deep into the lung, which has a much lower stopping power. Yeah, and then there is a second effect. So we have a scanned beam, which is moving, and we also have a scanned moving tumor, and these two motions interfere and cause a so-called interplay effect, which is just severe dose distortions. The movie that you saw was the dose to each phase, and if we accumulate that to a reference phase, then the outcome is a bit nicer, but not too nice. So all the yellows is underdose, which you definitely don't want to have in the GTV actually. So these are basically the challenges that we are facing. Yeah, this is some types of motion. Of course, there's breathing, yeah, which is the dominant motion. There's also heartbeat, which is typically ignored, but this also can be not irrelevant, close to the heart at least. And of course, there's something like peristalsis. This is actually in this animation, it's faster than the breathing, but of course, this is weekly CTs or daily cone beam CTs of the prostate, where you also can see that there's quite a lot of motion, not only in the organs, but also here in the soft tissue of the patient position. So the workhorse for analyzing motion is still the 4D CT with all its benefits and issues. Yeah, so you have a time-resolved quasi-static CT, typically divided into 10 phases, so 10 separate 3D CTs which depict the patient at some time points during his breathing phase. Yeah, and typically it is the case that this is a synthesized single breath. But this is taken over several breaths of the patient. Yeah, so and this can lead to imaging errors, which you can see here. For example, in this, there's this folding over of the tumor, which is just an effect that the patient had very different volume of breath while the image was taken. Yeah, and then you can divide this into phase-based. So just dividing the taken images into either phase-based phases or amplitude-based phases, which have both drawbacks and advantages. But so with all these caveats, this is still the main workhorse of analyzing particle therapy for moving targets, just because we need the range to the tumor. Yeah, so the CT is still the only modality which reliably gives us the range to the tumor. And so we are basically currently at least stuck with the 4D CT. And using these 4D CTs, we can register all the phases together. So here you see a false color image of the reference phase of end exhale and an opposing phase of end inhale of the same patient. Yeah? And if we register them and then deform the end inhale to the end exhale, you see that this red color vanishes basically. And this gives us both the opportunity, or the result that we're interested in is actually not the fused image, but it's the vector field that is underlying this fusion. Because the vector field allows us to propagate the dose over this motion, and it also allows to describe the motion in more detail than just measuring an amplitude. And what we can also do is we can use the inverse to contour to propagate contours from one phase to many, which is a great help to reduce the workload. So, and if we have these two ingredients, then we can actually go for 4D dose calculations. So we have so the 4D CT and the vector field. And typically we start with a 3D plan. Yeah, so just a standard plan delivery. And then what you, oh, the movie is not playing anymore. Okay. So what you then also need is the timing of the beam delivery. Yeah, you see here how the beam is scanning across this image plane. And now you can correlate this with an observed motion of the patient. Yeah, and now you can assign all of these points to different motion phases. Yeah, so you need a common time axis of both. And then you can divide the 3D plan into chunks that are delivered to each of these motion phases. And then comes in the 4D CT and the deformable registration. And now we can assign each of these 4D plans here to the corresponding 4D CT, compute the dose and deform it to a reference phase. Yeah, and then, for example, you can do these nice, this is still the undeformed dose, yeah, but you could accumulate this dose to the reference phase to get a 4D dose estimate. Yeah, and this is just why this is important. So this is the end exhale plan, and you see that the dose area is pretty large because this is planned for an ITV, yeah, which I will explain to you later. So the idea is that the tumor basically never leaves this this high dose area. And if you look at the 4D dose for this, then you see that just the smearing out of the motion reduces the size of the the high dose area significantly. So if you only have static images, even if you use static and exhale and inhale, and you estimate the doses to the OERs on the static images, then you will make a significant error. Yeah, and this is the 4D dose without considering interplay. Yeah, and if you consider interplay, then the picture will get considerably different. Yeah, so then you see these at least for a single fraction, you see these under and overdoses. So and this is something that still most available commercial treatment planning systems can't do. So even if you want to know what the effect of motion is for this particular patient, you just don't have the tool to assess this. Yeah, and this means you basically you don't have a good idea what actually happens, and you also don't know if what you do to mitigate motion actually helps. Yeah, because you also can't assess the effect of a motion mitigation strategy. Okay, so then to look into more detail into range variation first. Yeah, the issue is basically the following, that as I showed you already in this one movie, that the moving tumor itself in the lung causes significant range changes. So the color lines here are ISO range lines, and you see that over the breathing cycle, for example, this orange line traverses basically through half of the lung. Yeah, and as you want to irradiate not only the blue contour, but also a clinical margin around this, so the CTV around this, which is by definition in the lung tissue, this is a significant problem for particle therapy. Yeah, and of course this has to do with the Bragg peak. Yeah, if we misplace a Bragg peak, then the dosimetric effect is much larger than it would be for the same range change in photons. Yeah, so this is, for us, this is a significant problem. And of course, these range changes are field specific. So this is a bit of an involved graphic. Yeah, so you have here the beam angle irradiating some target from all around the patient. And here you have the motion phases in the 4D CT. And then the color map basically shows you where there are severe variations in range. Yeah, and here you have these three colored lines, which give you these, which are shown on the plot separately. And you see that there are some angles which are actually nice to use, and others which are not so good. Yeah, where the beam range will vary quite a lot over the breathing cycle of this patient. Yeah, and this is highly significant. So this is, in this extreme case, this is up to 15 millimeter change in water equivalent length, which is like 5 centimeter in the lung. So what is typically done to protect the target is to use so-called internal target volumes, ITVs. Yeah, and this really should protect the dose to the CTV from any motion-induced error. So, and this means you typically just increase the size of the target volume so that the CTV never leaves this ITV. Yeah, and this of course also means that you deliver more dose to the patient. This can be constructed in several different ways. What is often done is that you create either an average CT or a slow breathing CT, where you basically have the tumor smeared out over the breathing phase. Or you can also do an explicit maximum intensity projection from a 4D CT that you have, which works very well in the lung. So that basically you see the high density tumor in all of the phases. And this is just contoured. You can also fuse this with MRI or PET to get a better estimate of the tumor. You can also use a 4D CT explicitly. So you contour a reference phase, then propagate from this reference phase to all other phases using your vector field. And then you can define the ITV as the union of all these CTVs, which in the end is just about the same as using this maximum intensity projection. All these strategies are sufficient for photon therapy, where the range doesn't play such a big role. Yeah, but it does not consider range changes inside this ITV. And especially in the lung, this leads to significant dose errors. What a typical clinical strategy here would be to just replace the ITV with the density of the tumor, so that any lung that is in there would be replaced by a density that is basically around about water. Yeah, and the effect then is that even if there should be lung tissue in a given phase and tumor in another phase, you would still hit this tumor. Yeah, you can also have an explicit calculation of beam ranges over the felicity and use the union of this range calculation in water as a so-called range considering ITV. These two strategies are also not so different, except that this density replacement neglects any changes that occur in the beam entrance channel. For example, if there's a rip where the tumor is moving behind, then the second method would also capture this, but the density replacement would not. Yeah, and just to show you what the effect here is if you use the geometric ITV, so the photon ITV basically, yeah, then you can plan on your end exhale reference phase, get a very nice dose coverage. But if you then go to end inhale, you see that your target coverage breaks down, yeah, just because you did not consider the different ranges in this in the ITV. And if you change this to a range considering ITV, then you see that also the dose pattern changes, but you also can restore the target coverage in this area. The second effect is interplay, yeah, and this is basically a very nice or a rather old experiment from the Japanese, where here you have the reference dose as you want to have it, and now they vary both the scanning direction and the motion direction of this film, yeah, and then you get these kind of artistic renditions of the dose on the film just by overlaying these two types of motion. And you see this, the pattern is highly variable depending on how you actually do the irradiation. And as it's so variable, what can help to restore the dose is just to repeat the scan. Yeah, this is an example from GSI, where you have a static film and then one scan looks kind of horrible. And if you do more scans, then you approach the static case again. Yeah, this is not perfect after 10 rescans, but you can increase the number, and then eventually you will converge to the static case. This is a patient example for this. Yeah, so this is the interplay case. If you do 9 so-called slice-by-slice rescans, then you see that there's some residual underdose left. But if you go to a more advanced rescanning scheme, then you can restore the dose with 9 rescans completely. Yeah, and just to explain these rescanning flavors a bit, so that the basic approach is slice-by-slice rescanning. So you divide a given energy slice into several cycles that you want to traverse, so the number of rescans that you want to do. And then what you typically do is you invert the scanning path over this. So you go up, and then your beam would be here. And when you go down, you invert the scan path and go back down again. And then the second would then go up. You know, so just to avoid especially for our flavor of scanning, where we never turn off the beam, then you avoid large jumps over the patient's or over the scan space. Yeah. An alternative for this would be volumetric rescanning, where you don't rescan every slice on its own, but you deliver the plan completely, divided by the number of rescans, yeah, a fraction of the dose that you want to deliver, and then you just do it again and again and again. And depending on your machine parameters, this volumetric rescanning can be a lot more efficient to counter interplay, but it can also take a lot longer because you now multiply the number of energy switches that you have to do, and they can be significant in synchrotron machines. Another option, especially for spot scanning, where they actually turn off the beam switching between spots, is to do so-called isolated rescanning. So they only rescan large weighted spots a lot of times, and small spots that are also not so relevant for the dose delivery or for the accumulated dose are not rescanned. And the advantage of this is that you can basically keep the delivery speed high, because you can irradiate with a high intensity, and you concentrate your effect on those points that actually count. And last but not least is this so-called phase-controlled rescanning, sometimes also called breath-sampled rescanning. And the idea is that you deliver the entire rescanning cycle in one breathing period or in one gating window. Yeah, and this the background of this is that the idea that you want to have, or the trap that you can run into with this rescanning, is if you have some correlation between your scan speed and your breathing period, then you deliver the same points of your repeated scan always again to the same phase, and instead of mitigating interplay, you actually have basically a positive interference, and you escalate these dose spots. And this phase control rescanning is a very efficient way to prevent this. So basically, in this case, I just show 3 rescan cycles, but so for example, the Japanese typically use 4 or 8. Yeah, so you can also increase the number here if your machine is fast enough. So this would be the delivery of one entire energy slice, and the timing is planned to be during one gating window. Yeah, and then when you have the next gating window, you deliver the next energy slice with all its rescans, and so on and so on. Yeah, and this was shown to be highly effective to counter interplay. Yeah, the problem with this is that you have to be able to adjust your delivery speed to the breathing frequency. Yeah, so this puts some higher demands on the accelerator, but all the modern synchrotrons by now are technically able to do this. So this would be something that is not used in European clinics, but should be. Yeah, so this is the standard strategy of the Japanese by now. So to summarize motion, there is this interplay effect. Yeah, there is which is the interference between target motion and the motion of the scanned beam, and it can be compensated by rescanning in different forms. Then there are also these range changes, which can actually be much harder to compensate. Yeah, and one option would be to use this range considering ITVs. And important to note here is that the range changes are field specific, which also means that simple isotropic margins are not ideal because they will counter for every field the effects that are specific to only one field. Yeah? So the volume that you treat is actually then even larger than it has to be. And range considering ITVs plus rescanning are already a valid form of motion mitigation. Yeah, and this is also in use in clinical practice, for example, in Japan or also in other proton centers. Yeah, there is no standard implementation of how to construct the ITV and how to use the rescanning. And basically everybody uses what they can use depending on what the machine can do, what they experience with, and especially also what the treatment planning system offers. Yeah. And the drawback of this strategy is just an increased irradiation volume. Yeah, so counters this idea of precise delivery, but it allows you to give a very good target coverage. So then to go to more advanced motion mitigation techniques that actually aim for more conformal delivery, the very first idea is, of course, if we can reduce motion from the start, then the problem shrinks. Yeah? So one frequently used option is to use very rigid masks or this abdominal compression devices here, which actually, yeah, I mean, it does not look very comfortable, and I think it also is not very comfortable. But the idea is really to reduce and to reduce the motion amplitude, and also to make the motion more reproducible by basically forcing the patient to breathe in a specific way. It's important to note that this reduces motion, but it does not eliminate motion. Yeah, so the problem gets smaller, but it doesn't go away completely. Yeah, and of course, patient tolerance to this device is an issue, and also reproducibility of applying this device again and again in the fractions is an issue. Yeah, and there are several papers that report that this works very well and makes specific patient groups treatable with today's technology, and others report that this does not work very well, that it's not accepted by the patients, and that also the amplitudes vary and sometimes even increase when you apply this technique. Another option is beam gating, yeah, which I already mentioned shortly. So you just deliver the beam only when the tumor is in a predefined window. And this window can be defined again by phase or by amplitude. So if you know the tumor location in space, then this is much more accurate if you just have the patient breathing into some spirometer or so, which measures the motion phase. All flavors of gating increase the delivery time because you just limit the amount of time that your beam can be on. But for modern machines, this can be not a too large increase depending on how regularly the patient's breathing. There's always a trade-off between precision and delivery time. So the smaller you do the gating window here, the longer you have to treat, but also the smaller your margins are basically. And irregular motion in general is an issue. Yeah? So if you target a specific location in space and the patient is just not breathing where you want him to go, yeah, then this can actually cancel the treatment, yeah, and lead to sometimes very long treatment times. Another option would be deep inspiration breath hold. Yeah, so you just coach the patient into breathing in deeply, much deeper than you would do in normal breathing, and then hold his breath in a hopefully reproducible position for as long as possible. Yeah, and 20, 30 more seconds are possible with this, where you can basically reduce motion significantly and then deliver your beam without dealing with the motion issue. Yeah, and this is an example from a breast cancer irradiation where also one significant advantage is that you just reduce or that you increase the space between the delivery field and the heart. Yeah? And especially for breast, where the patients are younger, the heart dose is a significant issue because there can be severe late effects if the patients have a very long remaining life expectancy. This does not work so well in lung cancer, where patients have impaired breathing capability and are also typically much older. So compliance there is a significant issue. Something that actually is kind of natural for particles, because we scan the beam anyways, just to measure the motion, and then just change the motion of the beam that we do anyway to scan the tumor to follow this motion. Yeah, so basically you know where the tumor is and your beam just moves with the tumor while you're scanning it. Yeah, so this has been explored for a very long time, but it never left the research bench because you need a very accurate motion detection system here, and this is hard to realize in practice. And also, while this sounds natural, it actually is not so easy. Yeah, so we did some experiments at GSI already 10 years ago, where we were able to track a 3D moving target inside of this thorax phantom. Yeah, and we had a full tracking. That means we not only corrected the lateral position, but we also corrected the beam range. And we used some motion prediction model, and this could reduce dose error compared to interplay quite a lot. Yeah, so in the lab, it works pretty well. But if you go to real life examples, then the issues start to show up. Yeah, so one significant issue is that you correct only for the position of the brag peak. So in this very simple experiment, we have two films. One is here in front and is always static, and the other is in the back. This distal film here, and this will start to move eventually parallel to the beam. And if you have no motion, then both of them are homogeneous, so that's fine. If you start to have motion, then the front film remains homogeneous, but the back film starts to show an interplay pattern. And if we now turn on tracking, then yay, we can compensate this completely because it's just a simple translation. But now we basically put the interplay pattern that we before saw on the target, we put now in this first film, yeah, because we basically just invert where the interplay happens. So we compensate interplay on the moving film, and so we project it basically back on the static film. And typically this would be the chest wall. yeah, which is also basically not moving compared to the tumor moving behind the chest wall. So now we have a nice set of hotspots on the chest wall, which may not be so nice. Yeah, so we don't know the OER doses before we actually deliver the plan. The second issue is if you don't have a translation. Yeah, so this would be your back peak position, how you planned it. And now you have not only a translation, but also a rotation. And you can keep the planned location of the brag peak, but if the tissue before this rotates or deforms or whatever, then your planned entrance channel, which is this dashed line here, is replaced by this line. Yeah, so you still irradiate from the same direction, but your tissue rotated. You compensate for the translation part of the rotation, but you simply can't compensate for the rotation part. And this also leads to significant doses that are hard to compensate. Which leads us to a final idea of how we could implement conformal motion mitigation, which is 4D optimization of so-called multi-phase plan libraries. Yeah, so now we take a 4D-CT, which could have 4 phases. In this example, typically it has 10. Yeah, and then for each of these phases, we create one treatment plan which is conformal to our PTV in the phase. Yeah. And then during delivery, we switch between the plans and synchronize the delivery to the motion. Yeah, and the outcome is that we have plans that already contain the range changes that we expect from the motion, and that are that results in a very conformal delivery after all. And this also contains a form of phase-controlled rescanning, because you deliver the same dose in a controlled phase to this tumor again and again, which makes this much more robust than a tracking approach. Yeah, this is an example that we did together with CNAO. So we have the CNAO delivery system now at GSI, and we modified it to be able to treat these or to deliver these treatment planning libraries. And here in the top, you have the reconstruction of an experiment. So this is not a simulation, but it's a reconstruction of an actually delivered plan for flavors of this multi-phase delivery. And this is a 10 times rescan tracking plan, which does not look so good actually. And this is 10 times rescanned ITV, yeah, which has significantly more dose than the tracking plan, and also does not look so good because the motion here is irregular. Yeah, and in spite of the irregular motion, the multi-phase plans still work. And even if we have a motion drift in there, so here you can see the baseline is still stable, but here if the motion phase drifts away, then with a combination of multi-phase 4D, so 4D optimized treatment plan libraries and beam tracking, we can even compensate for this highly irregular motion, which is something that you would also expect to see in patients. So to summarize this motion mitigation part, there are several techniques at least in research available. Yeah, some of them are already in the clinic, and it's typically highly efficient to combine them. So rescanning with basically everything is always a good idea. Yeah, it sometimes this slows down the delivery too much, but rescanning always helps to reduce random errors. Yeah, and then you can divide them roughly into motion reduction, which are typically technically rather simple. Something like this DIBH, gating abdominal compression. The technical simplicity not necessarily translate into clinical simplicity. So sometimes these strategies have significant problems in the workflow because you need a collaborating patient. And if the patient can't comply, then all of these strategies typically have an issue. Yeah, and then more conformal motion compensations therefore try to shift the complexity to the technical space, which we actually have under much better control than what the patient is doing or able to do. And so something like beam tracking or 4D optimization could be more reliable to deliver conformal doses than these simpler methods, which are in clinical reality. Yeah, these are not. And a combination of both is the so-called MP4D, so multi-phase plans with tracking, could really be something that is able to conformal and robust deliver plans also to irregular motions that we expect to see in patients. Okay, I think to keep my timing, which probably runs a bit late anyway, I will go through the other two examples, and then we can have questions in the end. Yeah, so the second delivery strategy that I want to introduce is arc therapy. So arc therapy, as I already said, is clinically state-of-the-art in photon delivery. Yeah, so you really have the gantry rotating continuously around the patient, and also the multi-leaf collimator is operating continuously during this rotation, which allows you a lot of freedom in dose shaping. And it also is much faster than if you would deliver a plan of maybe comparable dose quality with IMRT, so with delivering several fields with a step and shoot strategy. And the idea is or the question is if we can transfer this advantages to particle delivery. Yeah, the first question, of course, does it actually make sense? Yeah, I mean, we can already deliver pretty conformal fields or pretty conformal plans with only 2 fields. So why should we go for arc delivery, which is then something new and more complex? The second, if that makes sense, can we actually deliver it? Yeah, because the existing gantries are so much heavier and larger than the photon gantries are. And then also, is there a feasible delivery scheme for this active scanning with multiple energy layers and potentially long switching times between the energy layers? Yeah, and if you have the patient rotating while you are switching switching energy, this is maybe not such a good idea. So one example that is actually going into clinical realization right now with the help of IBA is the so-called spot scanning proton arc, SPARC, yeah, where they actually also already delivered plans. So this is not only simulation, but also was actually delivered with a gantry system. And in their delivery, they showed that this works at least as good as the 3-field IMPT. Yeah, and the delivery was highly accurate. So here you see this is a gamma with a 1 millimeter, 1% to very high accuracy to the measurement. And the strategy that they are using is that they try to minimize the up switches of energy. So while they are rotating the gantry, they have to switch energy because the range to the tumor changes, but they only try to switch down because the down switch is something like 0.6 seconds on this device, and the up switch needs to cycle the magnets and takes 5 seconds. So whenever they have this star here, they could not avoid such an up switch, but otherwise they only switch the energies down. And on top of this, they also drastically reduce the energies that they are using. So they, over this 180-degree arc or 140-degree arc, they actually only use 97 different energies. Yeah? And a typical plan would already contain something like 30 energies or so. So the number of energies that they are using is probably comparable to the IMPT. And as they did not have to set up the different field angles manually, the delivery time was actually much faster than the 3-field plan. So basically for this realization, you could say that they achieved the 2 aims of faster and at least comparable dose delivery. If we think also of synchrotrons and ion machines, then it actually makes sense here to introduce to go away from the gantry and introduce chairs. Yeah, so the gantries for any proton or particle system are always big and expensive. Yeah, and this is even more true for heavy ions. Yeah, so on one hand, the gantries are very useful clinically. Yeah, so basically every proton center has them, and HIT, which has one of the currently 3 gantries that are operating in the world, has 2 fixed beamlines and 1 gantry beamline, but it still treats more than 50% of the patients at the gantry. Yeah, because it's just so useful. Yeah, but we could actually have the patient sitting and then rotate the patient in front of the fixed beam, which would at least partially replace the function of the gantry for specific cases that we still have to identify. And this has been discussed already for a long, long time. Yeah? So you see here basically more than 20 years ago, people were already using chairs and have been producing and proposing different chairs design again and again. But the game changer why this is actually useful now is that there's now also imaging systems, as you can see here, that allow to image the patient in the sitting position. So you don't have to image the patient lying down and then walk him to the treatment room where he's treated sitting up and everything just shifts down, yeah, and is the image is no longer representative, but you can image in the sitting position and use that for treatment planning. And I think this will lead to the acceptance of this chair systems in the next few years, just because they are so much cheaper than gantries. Yeah, this is an example. So here you also see in this cartoon the CT ring, the chair, which is actually mounted on this rather large 360 rotating base plate, and then a fixed beam line where the proton beam could come from or the particle beam could come from. And the peculiarities of this system from Leo Cancer is that they can also tilt the CT a bit, so they can adjust the incline of the patient. So he doesn't have to sit vertically, but he goes to sit a bit laid back, which is much more reproducible. And then they can also tilt the CT and measure at this angle. Yeah, and in principle, we could also rotate the patient while the beam is on, and that would result in an arc delivery. Yeah, which at much lower cost and at much lower technical complexity than if you have to commission different gantry angles and also especially the delivery while the gantry is moving.
Chris, we need to start concluding soon so that we give some time for questions.
Okay, I will try to hurry. Sorry. So for synchrotrons, the therapy, these switching of energies and also the non-continuous delivery means that you are even less flexible than with cyclotrons. But the very big advantage that carbon arcs might offer is that they increase the RBE in the target. Yeah, so I will skip this. We just devised the delivery schemes to deliver even less energies with carbon. Skipped. And this also results into very nice dose distributions where you can see, for example, here that the high doses in the brainstem are basically gone, but even more important, the high LET that the two-field plan here delivers to the brainstem is basically now shifted into the target. Yeah, and you see that the LET in the target reaches now very high values, and this could be useful against large hypoxic tumors. So this is something that we will continue to explore in the future. Yeah, so in principle, particle arcs are feasible, and I guess we will see more of them, especially from the IBA realization of the SPARC strategy. Yeah, and as I said, carbon plans might be useful against hypoxic tumors. Do you give me 5 minutes for flash, or should I skip this?
If you can shorten it a bit, it would be better, because we only have 10 minutes, well, 11 minutes left for questions.
Okay.
And I'd like to give you, otherwise, maybe we can field some questions now. And if there aren't any others, you can continue. What do you think, Chris?
We can, yeah, if you like.
So do we have any questions?
So probably
yes.
Now is
there we have one from Krista.
Yeah.
Thank you for the very nice presentation. Is I have two, but one I'll ask first. It was regarding the interplane, sort of the spot scanning for moving targets. So for there, the main thing from the technical point of view is just considering the rescanning. I was just wondering, is there like any things considered, or is it even needed, should sort of change the way how you scan the spot sequence? Because you showed, since some spot sequences result in bigger interpret results, I was thinking, is it something to be considered just to change up how you go from spot to spot for lung tumors or not?
So I think there's the variability of this is so high that it probably will be hard to say that there's a pattern form that is better than or just superior to some other, because it will vary a lot from patient to patient. But what you can do is actually you can basically sort the spots by size and then apply different rescanning patterns to your larger spot array and then to your smaller spot array. So similar to this isolated rescanning. Yeah, not sure if this answers your question.
Yeah, and if I may, also the other question was about the arc delivery. So I suppose from technical point of view, the idea is that we just give some energies from some angles and different energies from other angles, right? It's sort of changing both the energy spots and adapting everything from angle to angle. It's not that straightforward, I suppose.
So the idea really would be to find some energy that covers most of the tumor. So basically this red line here. Yeah, and eventually this. So you can think of this. It's not turning, whatever. So you can think of this as basically some form of inverse CT reconstruction. Yeah, you have your line and you scan it across the tumor, and you need to find a set of lines that cover all of the tumor with a set of different energies. Yeah, and here, for example, this green line was designed to change as few times as possible and still achieve like a good target coverage.
Okay. Thank you a lot.
And we have another question from Kyung-Don.
Yeah, thank you very much for your nice presentation about the motion control and so on. My question is a little bit more close to the clinical evidence. That is there any research performed to calculate or estimate the NTCP from motion controlling techniques?
So specifically for NTCP, I'm not sure. Yeah, there are very many dosimetric comparisons of different forms of motion compensation. Yeah, for example, there are pretty interesting papers from the Groningen group, which basically compare different forms of 3D and 4D robust optimization. And currently the status is that if you use clinical margins, so like something like 7 millimeter isotropic margins in the lung, then it doesn't really matter what you're doing, because the margins are so large that they also capture the motion somehow. Yeah, but I think the question will get more relevant if we start to shrink margins, which I think we have to do at some point.
Yeah, so I was just curious if there were some clinical research that showing the profit from those motion control techniques.
The problem is that that most of these methods are not in the clinic, right? So you also can't really do clinical studies on this.
I see. Thank you very much.
All right, well, there doesn't appear to be any other questions at the moment, and we still have 6 minutes left. So if you did want to maybe cover the flash section, if you agree, Nicholas.
Absolutely. Thank you, Chris.
Okay, so flash in 5 minutes. So actually I should take 150 milliseconds, I guess. So the idea of flash, I'm not sure, Nicholas, did you cover this in the week at all?
Not in enough of detail, though.
Okay.
It was mentioned a number of times.
Yeah. So the basic idea is that we switch from the normal delivery to extremely high dose rates. Yeah, and there is evidence that this changes the NTCP. So basically, the idea, this would not change the control, tumor control, but it would increase the tolerance of the normal tissue and then widen this therapeutic window. Yeah, and this is currently everybody's excited about this. And if you go to a meeting dealing with any form of radiotherapy, then it's flash all over. Yeah, so and the reason is basically now a growing number of preclinical studies that show pretty nice effects. So if you, for example, this is irradiation of pig skin, where a conventional delivery leads to this extreme severe side effects or you know, adverse events for the poor pig. And if you deliver the same doses with flesh, then you just have this mild discoloring and much reduced side effects. And the doses here are really extremely high, in the order of 30 gray in a single fraction. But the background is that you have to deliver like 100 times faster than is the clinical standard. And it's not really clear why this works, but it works apparently. And there are apparently some kind of thresholds which are thought to be now something like 40 gray per second, and at least 5 to 8 gray per fraction. And the standard treatment would be something like maybe 2 to 3 gray per fraction delivered in a few minutes. So you see this is orders of magnitude different. And this is of course a huge technical challenge, because how do you actually deliver this? So you have something like 5 gray and less than 150 milliseconds to deliver this large dose. And there are technical boundary conditions. Many of them refer to the accelerator. So the accelerator has to be able to provide this very high intensity. Luckily for us, proton cyclotrons are typically able to do this because they are scoped for the passive degradation of their energy to the lowest treatment energy. And thereby they typically lose something like 99% of the particles. So they are actually vastly over-dimensioned. But this is now a huge benefit because you are from the bat able to provide these flash intensities. And this is not the only thing. You also have to be able to actually deliver this. So the active components, something like fully active scanning with the energy changes, is just too slow. You basically, as soon as you start changing energies, you already violated your dose rate constraint. So you need something like either a passive modulation or a shoot through, which is currently the preferred method apparently in proton sphere, where you just extract the highest energy at the highest intensity and just abandon the back peak and just shoot through the patient. So, and also then monitoring, of course, and safety are problems. And if you look then, if we go back to shoot through therapy, then of course we start to see the dose again behind the tumor, and also a higher dose here than here, which of course this is due to proton scattering, that the dose is here higher. But the idea is that if the normal tissue tolerance is so much higher, then this could actually still be beneficial. Of course, we wouldn't use a single field, we would also use many fields, though it's not clear if the flash effect will hold up if you use multiple fields and they will cross somewhere, and if the crossing points are treated at different time points, if this still counts as flash or not. Then there are different ways of how to calculate those rates. Technical details, which I will skip now. What is a bit interesting, I think, is that there is a way to maintain the Bragg peak by using these so-called 3D range modulators, which is basically a 3D printed piece of plastic. I'll show you an example in a minute. And the idea is that you irradiate a single energy layer into this device, and it will modulate the beam so that the outcome is a spread out Bragg peak. And it's also opposed to the former passive delivery, it's conformal. So you see that this is really a sphere without those tails that you saw in the previous passive fluids.
She said.
For this, you need scanning because the intensity varies across the profile of this thing. So it's not an instantaneous delivery, but it can be very fast. This is such a device. You see it consists of well-shaped needles that you have to design and print. So it's also not so easy to manufacture this, but it allows you to recover the Bragg peak for flash. And this actually works. So this is an example in a small animal experiment where we just saw the delivery. And actually I think the blackening of the film takes more time than the delivery. So this was basically 20 grays delivered in less than 200 milliseconds, and in the SOBP. So this is something that really is able to make flash also usable for synchrotrons, which are typically limited in their intensity. Okay, so I think that there is a huge technical challenge to make this safe for clinics. Yeah, there is now a plethora of simulation studies which sometimes simply disregard this, especially this constraint here. And you have to think that this dose threshold is not in the tumor, it's in the normal tissue, because there you want to see the flash effect. So that basically means that if you have the typical leverage to the tumor, you need exorbitant single fraction or at least extremely hyperfractionated target doses. And that goes a bit against anything that we know from conventional radiotherapy, because you throw away the Bragg peak, you throw away the fractionation effect, which typically protects normal tissue. So it really has to be shown that flash is efficient enough or effective enough to compensate for these losses. Or you try to use these 3D printed modulators that recover the Bragg peak, but of course also means that you now have to have a patient-specific passive device again, which you have to print on time. And if there's a problem with the print, then whatever happens to the patient. So these are all unsolved problems, but I guess that we will see clinical studies with flash very soon. And of course, this could have very interesting implications for my field, for moving targets. So if this really works also for very large volumes, then I'm more or less out of work. If you can deliver this in 150 milliseconds, then nothing will move. And everybody can hold his breath this long. I mean, I would just switch fields, because you still have to make sure that the tumor is actually where you want to flash it. If you apply your very high flash dose and the patient holds his breath in the wrong position, this would also not be such a good idea. But still, it has nice implications for the future. Thank you for your attention.
Thank you so much, Chris. That was a very interesting talk. We will not take any further questions because we are somewhat tight with time. But I do thank you very much for for giving us your time for this very informative lecture. Thank you so much,